climate scientists Katherine Wentz and Rob Nelson. Thank you so much for joining us today.
Hello.
Glad to be here.
So I worked on sea ice cover in the Arctic and Antarctic. I use remote sensing, which I will get into in the presentation. Basically satellites that orbit the Earth. I use that data to tell me about how sea ice cover is essentially declining at the moment.
I work at NASA Jet Propulsion Lab, and I do a similar thing. We use satellites that go around the Earth, but I measure greenhouse gases like carbon dioxide and methane. And those, as you might know, can tell us a lot about climate change, the carbon cycle, things like that.
Oh, and I forgot to mention that I work at Remote Sensing Systems, which is based in Santa Rosa, California. Okay. So for the first part of this presentation, I will be focusing on my work. And then for the second part of the presentation, I'm going to do a Q&A with Rob about what it's like to be a climate scientist. Okay, so let's first dive into the science. So I entitled my talk From Microwaves to Sea Ice. And it's, you may not know what a microwave is. I mean, you probably are familiar with the appliance, the microwave, but microwaves are a form of energy that is emitted by the Earth. And we measure these with satellites over on the left-hand panel here. As I said before, I'm a research scientist at Remote Sensing Systems based in Santa Rosa, California. And I have a master's in environmental science from CU Boulder. Okay, so I'm starting with this image of magma. It's very hot, it's glowing. And what's going on here is when you look at this image, you see visible light being what we call emitted from the surface of the hot molten magma. So what is visible light exactly? A good thing to start off with when we're talking about light is the electromagnetic spectrum. This is how we characterize light. And we do this by the wavelength of light and the frequency of light. So wavelength and frequency are inversely related. That means that they're oppositely related. Wavelength is usually measured in meters. And we can have very long wavelengths of radio waves. These are about the size of buildings and humans. And then the wavelength decreases as we go to microwaves, which is my favorite type of light. That's the light that I work with, that I'm able to measure ice with. And then we go into infrared, which is actually the type of light that Rob works with to measure carbon dioxide in our atmosphere. And that's about the size of a honeybee, a couple centimeters. Infrared is even smaller. And then we go into visible. Invisible is the type of light that we are all very familiar with. That's what we see. And that's what the sun emits. And so you can think of like pictures. So say you take a picture of something and you look at the picture and you're looking at that visible light. But in some cases, you can take a picture using a different type of light. So for an example, an X-ray, that's a much smaller wavelength type of light. And that is able to go through your body and image your bones, your skeleton. And interestingly enough, even though we see in the visible region of the electromagnetic spectrum, some animals can see in different regions. So some animals can see things like butterflies can see ultraviolet light, snakes can see infrared light. You can think of infrared as the thing that we sense temperature. So a really hot object, that's giving off infrared radiation. And so these characterizations of light are critical in remote sensing of the Earth, of these satellites that orbit our Earth. They're taking basically photographs of the Earth's surface in these different regions of light. Okay, so I wanted to acquaint you with how light travels through media. And so this is a pretty simple physics diagram of light. Here we have the sun, that's our ambient light. And we have a target, the sun. Let's say the target is Earth's surface. And so a lot of sunlight that we see is actually reflected off of the surface of the Earth. So that's reflected light. Say, for example, you're looking at a plant and you see the color green. Well, the reason you're seeing the color green is because it's being reflected off that plant. Some colors of the visible spectrum, such as like red, are absorbed by parts of the Earth. And so when you have something that's absorbed, it can then be re-emitted. And that's what's in red here. And that's what I'm very interested in, is that emitted energy. And absorption equals emissivity. That's Kirchhoff's law. And then finally, you can have transmitted energy. So that's where you have a heat source. Maybe you're talking about like the core of the Earth, and the wave, that wavelength of light is able to go through media. And then all of these sorts of light are picked up with a sensor. In the case of our work, we're using satellite sensors. Okay. And here we have a diagram of the Earth, and that's on the left. And on the right-hand side is we're explaining what the Earth emits in terms of radiation. And so remember, the electromagnetic spectrum is characterized by wavelength. And so that's our x-axis here. And our y-axis is the intensity of that emitted radiation. So for the Earth, it primarily emits radiation in this infrared range, thermal. We can feel infrared. But it also emits in the passive microwave range, and that's not as well known. People don't realize, well, unless you're an expert in like these dynamics, you typically don't think of the Earth as emitting microwaves. But it does, and it's important for my research. Okay, so basically the camera we use are these satellites that have scanning microwave radiometers on them. So here are a couple videos that show two types of satellites, and you can see how so a radiometer, let me define this term, is it's basically a radiometer. So it's measuring radio waves. Microwaves are a subset of radio waves. Okay, so let's go ahead and play it and see let's first see how SMAP looks. And SMAP stands for Soil Moisture Active Passive Radiometer. You can see there's the Earth, and then the sensor is spinning, and it's scanning the Earth's surface, and it's taking photographs of the Earth's surface as it does that. So as you might imagine, it takes quite a bit of physics and math knowledge just to get that satellite up there in the first place, and get it positioned to orbit the Earth. And it orbits the Earth 14 times a day. The time it takes to rotate around the Earth is 90 minutes. And Aquarius, another satellite, can show you this really well. You'll see it orbiting the Earth. There it goes. So as it spins, it's also orbiting. And so we were able to collect this data and generate maps of the surface of the Earth, pretty much across the entire surface. You'll see in a second, we'll show you all of the orbits at once for a day. There it is. So hopefully you have a sense of, what sorts of tools we use to make these measurements. Now, we go from these photographs of the Earth's microwave emission to sea ice, to temperature, winds, etc. And I'm going to be talking about each of these, what we call data products. So we release a daily map of, we haven't released sea ice yet, but for example, temperature and winds, precipitation, etc. So a lot of different environmental variables of interest. But I do want to focus on sea ice because this is my favorite part of it all. This is what I work on an algorithm, a model to convert those microwaves to a measurement of sea ice. And how do we convert microwaves to sea ice? Well, let's focus on this left-hand panel for one moment. Here we have on our x-axis, this is our frequency of radiation, frequency of light. And this is actually, instead of wavelength, we're looking at, so it's what we call gigahertz is the unit. And so we have several different lines here. We have water vertical, water horizontal. Now, do not worry about vertical versus horizontal right now. It gets a little complicated, but just notice that for these two water lines, that the emissivity, the radiation the Earth produces in the microwave part of the spectrum, it increases as you get to higher and higher frequencies of microwaves. And now that differs from our two sorts of sea ice. We've got first-year ice, and that is also vertical and horizontal. In both cases are first-year ice. Just to clue you in, first-year ice is ice that melts in the summer every year. It has pretty much the emissivity with frequency does not change much. It's all highly emissive regardless of your microwave frequency. And then our third type is the multi-year ice. That type of ice stays around for multiple years. You can see that type, the emissivity of microwaves decreases as you increase your frequency of microwaves. So this is all to say that the Earth emits this radiation, but the radiation that's being emitted is unique for water, it's unique for ice, and even the different types of ice that you have. And so you're able to model it. You're able to detect first-year ice, multi-year ice in ocean. And so here we have an output example of the sea ice concentration from the National Snow and Ice Data Center. And the values range from 0 to 100%. You can see that in orange, we are given the median ice edge from 1981 to 2010, median meaning middle. So it's similar to the mean, but not quite. What's interesting is what is this? This is 2018, this is November 22nd, 2018. The ice concentration is much less in extent as compared to our median ice edge. So what that tells us is the ice is shrinking in the Arctic. And we couldn't do that without microwaves, especially because on the right-hand side here, the visible snapshot of the Earth is very cloudy, and microwaves are able to see through those clouds. So remember X-rays, how you can see through the body and look at the skeleton? Well, in this case, microwaves, you can see through the clouds and look at the ice and ocean. Okay, And I will show you a few other products of ours. We also do wind speed and wind direction at Remote Sensing Systems. This is an example of Hurricane Florence. And these are the different layers of, it's like the eye of the storm. And then of course you have really high 50+ meters per second winds right around the eye of the storm. And then they decrease as you get further and further from the eye of the storm. And we're able to actually measure that. So we can tell people almost in real time, okay, this storm is about to hit the coast of North Carolina, like for example here. You need to prepare, that sort of thing. So as we see hurricanes increase in frequency, I think this hurricane season, we've seen the most hurricanes we've ever seen in a hurricane season. This sort of data, which we also get from microwaves, is very important. Now we're also able to measure ocean salinity, and salinity is the amount of salt in the ocean. This is a fun video, and while you watch this video, I'd like you to point out two things. Do you see the Amazon River being discharged into the ocean, and do you see the Mississippi River being discharged into the ocean? When you think about this, remember our color bar here. SSS is the sea surface salinity, and lower values of PSU indicate fresher ocean, so less salt in your ocean. Higher values mean more salt in your ocean. So look for those two rivers, the Amazon and the Mississippi. Hopefully you're able to see the Amazon at this point. Right in here. And this is all from our data at Remote Sensing Systems. And the Mississippi, let's see if I can see it. Should be coming out here. Ah, there it is. So it's very exciting to see that our data is showing realistic dynamics. And up here, pardon me, northeast of South America, you can see the upwelling of colder waters, and they're less salty. So that's why you see a bluish cloud here, or I shouldn't say cloud, a bluish area. Okay, now, oops, pause this. Finally, I wanted to show our temperature data set. And this is of, again, interest to those who are weary of climate change. This is not so good news. So we have, let me go over this graph because it's not as straightforward as you might think. On our y-axis, we have the difference from 1980 to the 2009 average temperature of the lower troposphere. Now the troposphere is the layer of atmosphere that we live in, and that's the layer of atmosphere that is warming the most. And this is an anomaly, so it's the difference from an average. And when we see negative values here, what that tells us is, okay, these years were a little colder than the average, and that's in blue. And then the red are positive anomalies. Those years were a little bit warmer than the average. These years are not consecutive. Now that's the tricky part of this graph. They actually arranged it so that we go from the most negative anomaly to the most positive anomaly here. But something that you can easily see is that the negative anomalies are mostly in the 1900s. Do we have any 2000? Not really, nope. So all of our negative anomalies where it's colder than the average, is in the 1900s. And most of our positive anomalies are in the 2000s and beyond. Especially, you start to see 2017 had the second highest anomaly, 2016 had the highest. So that's interesting that we're seeing this trend that a lot of people are talking about. And we're using our measurements, we're using microwaves again. So we're actually measuring oxygen molecules that are warmer on average. And so when the oxygen molecules get warmer, they emit more microwaves. And usually, so beforehand I was talking about how the Earth surface is emitting microwaves. Now in this case, the atmosphere is the one that's emitting the microwaves. Okay, so what's the importance of this work? Well, it's very informative of a changing planet. We have what we are now calling the climate crisis. Youth activists in Europe, now in America, are all rising up. They're saying, look at the data. This is not good for us and our future. We're the young ones, so we're going to be the ones who are deeply affected by a warmer climate. We're seeing wildfires in California. We're seeing, like I said, the most hurricanes out of any season before. The Arctic ice is shrinking. There's a lot of signs out there in the data that are worrisome. And so this is why it matters. And this is why it really matters to have an accurate data set. So whether you're a scientist or an activist, there is something that you can contribute. And I think scientists, hopefully we can support the youth who are, especially Greta Thunberg, who are upset. And it's interesting too, because it's an ethical question. It's not just a science question. We know it's happening, but is it ethical that we are hurting the planet for future generations? And that's a very interesting question to me as well. So yes, that's it for my presentation. And maybe you're inspired by the science, but you could also be inspired by the activism. In either case, there's a lot to be done. So thank you very much.
Thank you. So we have quite a few questions here from Carrie. How quickly is the satellite moving?
So the satellite orbits the Earth 14 times a day. And gosh.
It's a few kilometers a second. So like over a mile a second. They're moving super fast.
Jason asks, are photos in clear weather ever used as evidence of declining sea ice? Is the microwave data corroborated with photos occasionally?
Oh, yes. I spend a lot of time on this website called Worldview, where they have visible imagery of the ice. And I will look at my data set of sea ice and compare, like, okay, in Hudson Bay, do we see that as ice? Or it's hard because it's mostly cloudy, but there are times when it's like clearly that is ice, and you can actually see like the striations in the ice as an indicator. It's all investigative work, so it's a lot of fun.
Aaliyah asks, when testing the salinity of water, do you have testers set in the water, or how do you get that constant changing data? Right.
We have buoys that we pretty much test our remote sensed data with. The buoys are scattered around the globe. They're mostly in the lower latitudes, so closer to the subtropics and tropics. But those are what we call our point in situ validation. So we think that the buoy that measures the actual water, that is the closest thing to truth that we have. And then we base our models off of that.
How accurate can the satellite data be? Are there factors that will make it more or less accurate?
That's a very good question. We spend a lot of time in this field doing error estimates, uncertainty analysis. There's things like that have to do with the actual machine, the sensor that can throw off the data. And then there's also inputs into our models like cloud liquid water content, rain. Rain is a huge factor that creates error in our data set. So that is a whole project that people work on. It's just error analysis. Yeah, we spend time doing that.
So global mean temperatures are measured by looking at oxygen rather than thermometers?
Right. Well, in our case, it's oxygen molecules because we are using our satellites to look at it. But what do we compare it to?
Yeah, so in general, you can measure the temperature of the Earth in a whole bunch of different ways, and the most common one, like you just said, is a thermometer. So we've had thermometers in a lot of places for a long time. So the most robust answer to is the globe warming is looking at those really long records of thermometers. But since the 70s, we've been able to measure temperature using a number of different satellite methods, including using microwaves. So now we have this almost 50-year satellite record that we can say, hey, look, this agrees with our longer thermometer record that the temperature keeps going up and up. So yeah, we have a bunch of different ways of doing it, and using the emissions from oxygen molecules is just one of the many ways.
Yeah.
Seraphim asks, have older ice patches been spotted more frequently at the poles? What kind of ice is seen more commonly due to climate change? How are the satellites able to measure the age of the ice?
Right. So we're actually seeing a transition from that multi-year ice that sticks around for many, many years to the ice that melts away every summer. And that's actually a change in thickness. So multi-year ice is really thick. I think it's just been like around for so long. It just gets thicker and thicker and thicker. And then it becomes thinner as its first year ice. Now, what that means is that more and more ice is melting in the summer, and polar bears, seals need ice to birth and to raise their offspring. And in the summer, I'm not sure what season they do that, but I imagine if there's no ice in the summer, it would be difficult to do that. So that's actually a really good question. It has important implications. In terms of how we measure it, the interesting thing about multi-year ice is that the salt drains out completely. So first year ice has a little salt in it still because it's ocean water, right? Ocean water has salt. So you get your first year ice, which has some salt, and then over time the salt drains out, and that leaves little air pockets in the ice. And your microwave emissivity, that emission at higher frequencies, actually gets scattered in the ice because that wavelength is just the right size. It gets scattered in the ice. And
by the air pockets.
By the air pockets, yeah. And so you don't have, from the satellite perspective, you don't see as much emission at that select high frequency of microwave. So yeah, it's like very detailed, but it's actually a really easy signature to disentangle. So it's not often in science you get such an easy thing to disentangle.
Carrie is wondering, despite obvious bad news with climate change, is there any recent good news in your field?
Good news.
Yeah, we take a crack.
Sure.
Yeah, of course, there's certainly good news. We see that the sea ice is melting and the temperatures are going up, but the world is rapidly moving towards renewable energies, and I think Europeans and Americans, everyone across the world is understanding that renewable energies are sort of the future of energy, and that's going to start to chip away at how much greenhouse gas we're emitting. So hopefully over the coming years, we're going to start to decrease how much we're emitting into the atmosphere, and that will in turn start to help out with global warming. So yeah, there's certainly hope.
Well, you can also see, like, we're in Los Angeles at the moment, and the number of Teslas has increased so much since a few years ago. So electric cars that's one way to reduce your footprint.
Sophia is wondering, can artificial microwaves affect the readings?
Oh yeah, that's a really smart question.
Great question.
Yeah, so there's this thing called RFI, and it's radio frequency interference, and that definitely throws our measurements off. And that's being there. So actually, scientists come together and we're like, okay, did you find an RFI spot? Okay, I found an RFI spot, and it's right here. And what is that RFI coming from? It's coming from like our phone towers, right?
Cell phone
towers, and I don't know what else. But anything that humans are using for communication devices is usually in the radio region. And as you know, what is the newest thing? The 5G.
Mm-hmm.
5G. It's like in a certain radio frequency that actually microwave scientists are a little bit like agitated by, because we need these windows of microwave radiation to make our measurements, but the cell phone networks also need it. So
yeah, fortunately you don't have to worry about your microwave in your kitchen because it's not very powerful.
yeah,
So that won't matter.
So could you tell us a little bit about the journey that you took to get to the work that you are doing now? Do you have any words of advice for students, particularly girls, who might be interested in becoming climate scientists?
Well, we were going to do a little Q&A with Rob, but this is actually better.
You got to tell your story.
My story. Okay, my story. So I'll have a similar story, but I actually went down the master. So let me start from the beginning. So I went to school at UC Santa Barbara, and for my undergraduate education, college, and I majored in. I started doing environmental science, but I actually switched to earth science. I liked the math courses, and I really liked geology. Now, the next thing I did was during my college experience, I did some research opportunities. I was an intern for a woman who was doing paleoclimate research. So that's like looking really in the past at climate using what we call proxies, isotopes. And then I also did some research for a woman who was analyzing the geochemical contents of these barrels at a company called Montrose Corporation. They just dumped their residual waste into the ocean, and I was doing a geochemical analysis of that. So I've done a lot of things, and then I went to school for my master's, actually for my PhD at CU Boulder for environmental science, with like very strong science emphasis, computer modeling. I had to learn to code because that seemed to be where the field was going, hence our exercise we're going to be doing in a bit. And this is a good story. So I was going to do a PhD, but I realized that I did not want to go into academia, meaning I did not want to be a professor, and I didn't want to study a really, really narrow topic. I wanted to kind of apply my skills more broadly. And so I went to work for remote sensing systems after I decided just to get a master's. I decided that like my second year in, I was like, I'm just going to do a master's. And it was a kind of a rush at the end, but I got it all together. And at the time I was doing biogeochemical modeling, computer modeling, and that involved climate change, but also how do plants respond to climate change, and especially in the alpine tundra. So basically, throughout my career, I had an interest in climate science, and then I started working for remote sensing systems after I got my master's. And the nice thing about having a master's and working at a private company is I was able to sort of, I guess, like, it is even though I'm studying sea ice and it's narrow, I get to work on projects with sea surface temperature. I get to work on projects with the salinity stuff, and it's not as focused on writing papers. It's more focused on getting data out to people. And so in my mind, it was a broader kind of application of climate science. So there's so that's that avenue. You can go down and get your master's and work more in like industry, which might feel more applied and more broad, or you can get a PhD. Mm-hmm. Do you want to talk?
We can talk about that.
Okay.
How about advice for young girls specifically?
Oh, for girls? You're just as smart. Really, though, it's a confidence thing. A lot for me, it was a confidence thing that I can do this too. I am getting just as good of grades as the boys, and I also like math. So having confidence in yourself and seeing yourself as that you can contribute to this world of science. It's not outside the realm for girls. Like, this is, I don't know how to explain it, but I don't know how to explain it. It's just, your value isn't just tied to how you look or how you appear. It's the value is tied to what you're interested in, and in my case, it happened to be math and science, and so yeah, that's what I have to say. So I'm gonna do a little interview with Rob about his career trajectory, because he went more down kind of down the academia route. We'll get into it. So, all right. Hello, Rob Nelson.
Hi.
What inspired you to go into your field of science?
So I'm guessing everyone in this class, you guys are high schoolers and middle schoolers for the most part, and you probably have some interest in science. Mine came about at a pretty young age, but it wasn't until I think I took a few classes in high school that it was like, this is really interesting. You know, you're learning something about the world, whether it's geology or, in my case, meteorology. I was really fascinated by, thunderstorms and tornadoes and things like that. So when it came time finishing up high school, I was like, well, I should, probably go to college because I want to learn more about one of those topics. And I decided on meteorology. So I went and searched around. I'm from Minnesota, so I searched for a school in the area, a couple of schools in the area that had a program in meteorology, and applied for one and got accepted, and then went and got my bachelor's in meteorology there. So yeah, I think just finding something you're passionate about, and if you're just passionate about science in general, you could, one good path is to, go to a local school, or, if you get a scholarship somewhere, go there and take a few classes, take a geology class, take a biology class, take a meteorology class, and see what really you're passionate about. And then you can follow that trajectory. You don't have to decide right now, I want to major in theoretical physics. You have a little bit of time. If you decide to go to college for a science degree, you have a little bit of time to make a decision of what you're most passionate about.
I think that's great advice. What is your favorite part of your job?
So I might have said earlier, I work at NASA. I work at the Jet Propulsion Lab down here in Pasadena, in outskirts of Los Angeles. And I think the best part about my job, besides learning more about science every day, is working with a bunch of other people who also love it. Like you're sort of lucky if you end up in a place where everyone thinks, everyone's as passionate about you as what you do. All these other scientists, they have, college degrees, and they're science nerds. They love space, they love weather, just like I do. So I get to work with these people every day on my specific projects. And it's really a great time.
And we get to work with each other now
We
that we're in quarantine.
Now everyone's working from home, so it's a little different, but we'll make do.
Yeah, good thing we're both really into science, so it works. Okay. What sorts of job opportunities are there for a scientist?
That's a good question. So you guys are in high school, but it's never too early to start thinking broadly about what you want to do with your lives. I know a lot of people, when they're pretty young, so my background is meteorology. I got my bachelor's degree. So right after high school, you go and get a bachelor's degree. I got that in meteorology. And a lot of my classmates, when I went to Iowa State, they were like, I want to be on TV. I want to be the meteorologist on the Channel 5 news at night. And they knew what they wanted to do. So for them, it was sort of easy. But for a lot of us, you're not quite sure what you want to do in the future. So I would recommend just having an open mind, talking to people higher up, like talk to your teachers, talk to people you meet in the field, and ask, what do you do? Like, what do you like about it? What don't you like about it? And like someone asked in the chat, they asked Katherine how she got where she was today. That's an excellent question to start asking people now. You can find, if you go to a conference or a meeting and you find someone who you're like, oh, they do really cool work, their job sounds cool, go up to them afterwards and ask, how'd you get there? Did you get a bachelor's degree? Did you continue on to get a master's? Did you keep going and get a PhD, or did you stop somewhere? So I think that's a good way to go about it. Yeah.
Just like have that curiosity and be willing to explore and pursue what's interesting.
Yeah. And another thing I would say is you'll a lot of you might go to college and major in geology or some field of science or something else, whatever you're passionate about. But then you have the option, as Katherine was saying, to go and get a graduate degree, which is oftentimes what you want to do if you want to focus in more on a specific topic. If you want to end up doing being a professor at a university, you'll typically get your bachelor's degree, your master's degree, and then a PhD, and then a postdoc, which is what I'm currently finishing up. And then you can go become a professor at a university. But there are plenty of options if you want to stop anyway along that education journey. If you want to stop after your bachelor's degree, there's plenty of jobs available from companies or research centers, things like that, at all parts of the path. Like, you don't necessarily have to go and get a PhD to get any job in chemistry. Like there's all sorts of, and so that goes back to talking to people and say, hey, what did you do? And is that the right path for me? Do I really want to go all the way and get a PhD and a postdoc and whatnot?
Yeah.
So.
Yeah. I know a lot of people, I don't know a lot, but I know some who went the communication route. They got degrees in science, but decided they actually just really like talking about science. They didn't actually want to do the research. They just wanted to celebrate it. And so there's journalism opportunities too. So if you like writing, don't be afraid to go into science. There's still opportunity there. Okay. And then finally, do you have any advice? I mean, you have been giving lots of advice, but do you have any like specific advice for aspiring scientists?
Yeah, I would say these days, try to take as many classes in coding, math, and physics. I think those are the big three. I think we have a math teacher viewing right now, but lot of science is based on how the world works, and you describe that using mathematics and physics, and you develop those tools using coding. So I code in Python. Katherine uses Python, but also other languages. There's a whole bunch of languages. I would personally recommend Python. I think it's very versatile. But yeah, math and physics and coding. So if you get an opportunity in high school, or I don't know what they're doing these days, but early in college, the sooner you take an introductory to coding, the better, I think.
Yes, which is actually a good segue into our assignment that is written in Python. Shall we move on to that? Okay.
I thought I saw, was there a question at some point? We can't hear you.
I think that's a good segue as well, because the question was about the intersection between computer programming and climate science, and I think that this exercise will illustrate that well.
Yes. Yes. All right. Well, should I can go through it by sharing my screen. Okay,
Yes.
I'll do that.
And yeah, while she does that, I would say that they're very intertwined. It was not like that maybe a few decades ago, but now because we have these satellites that take huge amounts of data, you really need to write code in a programming language to be able to effectively analyze data. Back in the day, they'd take 5 measurements in the Indian Ocean and write a paper or publish some amazing results on that. But now we have the satellite I work on, the Orbiting Carbon Observatory, makes 1 million measurements of CO2 a day. So it's impossible to do anything with that by hand. You need to know some sort of coding language so you can load in the data, plot it, think about, analyze it, things like that.
Yes.
Which Katherine's tutorial here is going to show you guys how to do.
Okay, so if you all can go ahead, and I've heard you've downloaded Trinket. If you could pull up your Trinket. And Milo, did you send them the zip file?
Yes, and if you haven't downloaded it, it's on our class site. So you can download those files on the class site. And I'll put a link in the chat to that class site for anyone who doesn't have it.
And this is all being recorded, right? So they can go back and watch Katherine's demonstration again?
Yes.
Okay,
Oh, great. Great. Okay. So the first thing that you do once you're on your Trinket homepage, you've logged in and everything, is you're going to go ahead to this blue button up on the right-hand side up top here called New Trinket. Click that, and I want you to open up the Python 3, not the Python 3. That's important because I write all my code in Python 3. And that's what the example is in. Okay, so once you have your Python 3 loaded up on the screen, you're going to need to import your files that I gave you. Now, if you have a zip file, it's pretty easy to unzip it, and on MacBooks, you just double click the zipped file and it will give you the folder with I don't know if it's under, I think it's just the different files that will, the folder contains the files you'll need. And so I've already unzipped mine, and what I do to load it into Trinket is, I think it's this, okay, so you click this button that has an upward arrow, upload text file. Now I'm on my work. I need to go, I'm navigating through my computer right now.
I'm guessing people know how to do that.
Okay.
Kids these days.
Yeah, they're pretty smart.
I guess if we were your age, we would struggle through this because we were just coding and things were just becoming more popular, and not everyone had a personal computer and things like that.
Okay, yes. So now that you found wherever you've stored your zipped file, here, for example, oops, pardon me, messed that up. Go back. So you'll have to input first the graph cice.py, open that up. Okay, exit out of this little message. Now, something that you need to do, it's a little annoying, but to make it work, you're gonna go ahead and copy all of this, all of the Python file you just imported, copy, and you need to put it into the main py because the code runs the main py, main Python file. Okay, so once you've done that, you can actually go ahead and exit out of this by doing this little trash can icon. Beep. All right, now that. So now we have the code under main. And then we'll also, to run the code, we'll need to upload the ice extent and ice concentration files. And so they are ordered from 1 to 12. And I bet you can guess what that means. So January through December. Now, for my demo, I'm going to just do 2 of them. I'll do January, open that one up. And then I'm going to also open up, let's do July. Open.
And for anyone joining on YouTube, these files will be on the Sonoma Library Mind of a Scientist site. So you can download them there.
Great. All right, so now I've got my 2 files open and my main script. I should be able to run it. But before I do that, let's just take a look at the files. It's always good to, if you can, look at what you're about to plot. So here we have years. Okay, so here we have years from 1988 all the way through 2020. Month is all going to be 1 January because this is the January file. And we've got our data type. Don't worry about that. Goddard is a place that generates the data. Region is N, and that stands for north. So we're looking at the Arctic sea ice. And then here we have our extent and area. Extent refers to the sea ice, how do I explain this? It's kind of like how far the sea ice extends in the Arctic. And area refers to the total, I think it's million
square kilometers.
Million square kilometers, yes.
So 12 million square kilometers.
Which is quite a bit. Okay, and that's, both files are going to have this format. And you may notice you have some odd numbers here, negative 9999s. That means that the data is missing. And we're going to deal with that in the code. Okay, so let's go to the code. I will walk you through it. Oh, yeah, I'll give you a general walkthrough and have you independently look at the details. So here I describe the assignment. I'll read it briefly. First, download the monthly data from the zip file. Second, read and graph the data using this code. Third, figure out which month of the year shows the greatest decline in sea ice concentration from 1988 to 2020. And then I would like you to report back. Okay, so that's the general assignment. And here I have lots of commenting in green. This is not run by the code. We need to import some libraries here. And this is helping us with plotting. It's helping us with some calculations and helping us with the handling of the data that is right now, it's a CSV file. And we need to handle that in Python. And pandas is used for that. Okay, and so first let's give the file a name. And that is, has to be exactly the same name as what is given here. So I have in 01 extent version 3. If that's not the exact correct text, you will get an error. So month is January, and these are both in quotes. And now what you're going to do in this assignment is you're going to be changing these two things, because you want to look at all of the months and you want to see which month has the greatest decline in sea ice concentration. Okay, so next step, you're going to go ahead and read in your file. In this block of code, we are dealing with these negative 999s, and I will let you read through this on your own. We use print statements a lot while we're what we call debugging. So debugging means going through the code, figuring out if there's any errors, making sure the code is running the way you think. So we're going to go ahead and print that, and you'll see the output print. Once you run this file, you're going to see an output here on your right-hand panel with a lot of numbers. Now, finally, we're going to make the figure. Now, I want you to make a figure before you figure out which month shows the greatest sea ice concentration decline. It's a good way to visualize the data. And this is how you make a figure. I'm going to let you look at that on your own. And then plotting onto that figure you just made. Again, I'm going to let you take a look at that. And then finally, what I'm showing from line 67 on through line 88, this is a model. This is how we do a linear regression. Now, I could have just done a quick function call from, say, scrolling up for a second, say from import numpy, I could have done some sort of numpy.regress. When you have a dot something, that typically means it's either going to do a function or it's a variable that corresponds to numpy library. So these libraries do have linear regression functions, but scroll back down, I wanted to show the model as is, not in function form. I wanted to lay it out for you because this is kind of the gist of my work, really, is modeling things. And you have an input, you want an output, and that's what a lot of times you use code for. So don't worry too much about totally understanding it, but if you want to learn something challenging in coding, if you've never coded before, you want to learn something new, this is a for loop. And take a look at that, maybe do some print statements, and try to see what's going on there. I'll leave that up to you. And then finally, we run this model, and what this model generates is our M and C, where M is the slope and C is the y-intercept. A linear regression, pardon me if you may not know what that is, that's just making a line, a trend line out of, say, like a scatter plot of data, or data that it's not linear. So we have to derive a slope, intercept, y equals mx plus, usually I say b, in this case it's y equals mx plus c, a little confusing. So you're able to then, in this line 97, you can predict your y, you can generate y values using this m, modeled slope times your x. Higher up in the code, you declared this x variable, and plus your intercept. And then you're going to plot that predicted line. And I'll let you, like I said, I want you to sort of go through it yourself and try to figure it out. Okay, and so you'll have all the information that you'll need to figure out which month shows the greatest sea ice concentration decline. And I will, for example, I will show you how to run it. So all you do is click run. If this works. Looks good. So we have some outputs there. another output. And these are corresponding to our prints. For example, let's see, where was this printed? Ah, right here, print M and C. So this is slope and intercept. And what units are these in? That's a question. So the units, because this is we're graphing sea ice concentration that's in million square kilometers. So it's per month of, sorry, it's per year.
It wouldn't be per month.
Well,
that isn't on.
the data is for January, right? It's just for 1 month.
Per year.
It's per year, yeah. And so if you think about it, your line, which I'll show you down here, that's your line that you model. Now that's going to have a slope of your million square kilometers change per 1 year. And then the intercept is going to be million square kilometers units. So, okay, I'm going to let you all loose on this. I think that's enough explanation for now, and the code is commented quite a bit. So I'm going to go ahead and stop sharing. And now I guess we'll give some time to the students to work.